Hello friends, I am Adeesh Deshpande from Fergusson College. We are discussing Ionic Equilibria. Today we are going to study solubility product. Now in the last class, as we saw common ion effect and buffer solutions, where I told you that this is the part which is related with our practical chemistry. Now today we are going to consider yet another part which is also related with our practical chemistry. So that is solubility product. Now before we find out what is solubility product, let's find out first the meaning of few terms. The very first term is sparingly soluble salt. So the salts which have negligible solubility in water at ordinary temperature. Such salts which are practical are known as sparingly soluble salt. The examples are given: AgCl, silver chloride; AgBr, silver bromide; AgI, silver iodide; then PbS, lead sulfide; PbSO4, lead sulfate; BaSO4, barium sulfate, and etc. So these salts, if suppose silver chloride is taken and suppose water is added to silver chloride, then this silver chloride remains undissolved. So it is practically insoluble in water. For example, if 100 molecules of silver chloride are taken, hardly 1 or 2 molecules are dissolved. Remaining molecules are undissolved. So undissolved means they remain as it is, becomes insoluble. And so any salt, whenever dissolved in water, there are only two possibilities. First is the salt gets completely dissolved in water, and other is salt gets completely undissolved, remains insoluble in water. So first part we know, the second part we are basically considering. Now in the second part also, the substance will not remain as it is. Very few molecules of that salt always get dissolved, that is, they enter into the solution forming ions. But since, as I told you, that out of the 100 molecules, hardly 1 or 2 molecules are dissolved, that is, they enter into the solution forming ions, almost 98 molecules remain behind. So 98 is very close to 100, and therefore such salts are called as sparingly soluble salts. We are not saying completely insoluble salts. Instead of this terminology, we are going to use the term sparingly soluble salt. And this solubility is considered as negligible solubility or practically insoluble in water. And so such salts are sparingly soluble salts. Now one more term we have to consider, that is saturated solution of sparingly soluble salt. So a very small amount of sparingly soluble salt, whenever shaken with water, most of it remains undissolved, and whatever little amount of it goes in the solution makes the solution saturated. In this solution, salt is completely dissociated. So again, by taking the same example, out of the 100 molecules, just 2 molecules are dissolved, and with these 2 molecules, the solution which is present is called as a saturated solution of that sparingly soluble salt. The 2 molecules which entered into the solution, there they get completely dissociated, forming their ions. So a very small amount of any sparingly soluble salt, whenever shaken with water, most of it remains undissolved, and whatever little amount of it goes in the solution, makes the solution saturated. This solution is called as saturated solution of that sparingly soluble salt. In the solution, salt gets completely dissociated. Now let's consider this definition of solubility product. In a saturated solution of a sparingly soluble salt, the numerical product of equilibrium concentrations of ions raised to the suitable power is constant at a constant temperature and is known as solubility product constant. The definition can be explained by taking the example. So let us consider first example, that is, consider a sparingly soluble salt silver chloride dissolved in water. The following equilibria exist. AgCl solid reversibly gives AgCl saturated solution, reversibly gives Ag plus Cl minus ions in the solution. Again, to understand this, take the example of total number of molecules, which I said silver chloride 100 molecules I have taken, out of which 2 molecules entered into the solution. So saturated solution, middle part is AgCl saturated solution. Here 2 molecules which entered into the solution. These molecules form their ions. So equilibrium is actually present between AgCl solid and Ag plus and Cl minus ions in the solution. Now as equilibrium is attained, you can apply law of mass action to calculate equilibrium constant. This is exactly on the similar lines as we saw earlier for weak acids, weak bases. Likewise, if I apply law of mass action here, I will end up with the equilibrium constant K, which is equal to active mass of Ag plus into active mass of Cl minus upon active mass of AgCl solid. But we saw in the earlier part that most of the solid remains undissolved, and so concentration of AgCl solid, that is the denominator term, that I am going to consider as constant, because 98 molecules which remain behind is almost same as that of 100 or very close to 100. So this I am going to consider as constant. So K into constant is equal to active mass of Ag plus into active mass of Cl minus. This is a new constant called as Ksp, and so expression is Ksp is equal to active mass of Ag plus into active mass of Cl minus, where Ksp is called as solubility product constant. So you can understand, students, here that Ksp itself is the equilibrium constant. So from the final expression you can make the definition of solubility product. So on the right hand side, concentrations of Ag plus and Cl minus ions are present. These are molar concentrations. Further, these are the equilibrium concentrations. The product, numerical product of these equilibrium concentrations is considered. So this numerical product of molar concentrations of ions in the saturated solution of this silver chloride, this numerical product is always a constant Ksp on the left hand side, which is called as solubility product constant. So once again, let's go through the definition. In a saturated solution of a sparingly soluble salt, numerical product of the equilibrium concentrations of the ions raised to the suitable power is constant at a constant temperature and is known as solubility product constant or simply solubility product. Now let's consider a general sparingly soluble salt BXAY, which is dissolved in water. So following equilibrium exists. BXAY solid reversibly gives BXAY saturated solution, reversibly gives XB raised to Y plus aqueous. plus Y A raised to X minus aqueous. These are ions in the solution. So if I apply law of mass action, equilibrium constant K is equal to active mass of B Y plus raised to X into active mass of A X minus raised to Y upon active mass of B X A Y solid. Now active mass of B X A Y solid is a constant. So K into constant is equal to Ksp is equal to active mass of B raised to Y plus raised to X into active mass of Ax minus raised to Y, where Ksp is called as solubility product constant. So remember students, in the equation, if you saw the equation again, then in the equation, coefficient of cation is By plus, its coefficient is X, and coefficient of anion is Ax minus, its coefficient is Y. So to balance the equation, it is essential to write these coefficients. These coefficients represent the number of moles. So I can say that X moles of cation By plus are present and Y moles of Ax minus, that is anion, are present. Remember students, in the expression of solubility product, these numerical coefficients of cations and anions, they always appear as the power in the expression. And so in the final expression, you will find that active mass of cation is raised to the power X. From where that X has come from the balanced chemical equation. Similarly, in the expression, active mass of Ax minus raised to Y, that Y is the molar concentration or numerical coefficient in the balanced chemical equation. So these numerical coefficients or number of moles which are obtained from the balanced equation, those always appear as the power of the concentration terms in the expression of Ksp. Let's consider some of the examples. First example is Bi2S3. This is bismuth sulfide. So find out what is X and what is Y. So X is equal to 2, Y is equal to 3. Compare with BXAY as our general sparingly soluble salt. Now to write the expression for Ksp, Bi2S3 solid reversibly gives 2 moles of Bi3 plus aqueous plus 3 moles of S2 minus aqueous, ions in the solution. So bismuth cation has 2 moles, sulfide anions have 3 moles. Now the total charge, positive and negative charge, are balanced and our equation written is right. Now what is our general expression of Ksp considering BXAY salt? Ksp is equal to active mass of By plus raised to X into active mass of Ax minus raised to Y. So substitute, cation is Bi3 plus, X is equal to 2 and Y is equal to 3, and anion over here is S2 minus. So expression is Ksp is equal to active mass of Bi3 plus raised to 2 into active mass of S2 minus raised to 3. So whenever you are given any particular salt, always first find out what is X and what is Y. And if you have written or if you know the general expression of Ksp in terms of BXAY salt, then it is possible to write the expression for any particular salt given. Let's consider one more example, that is example of say calcium phosphate Ca3PO4 twice. Find out X and Y. What is X here? X is equal to 3, Y is equal to 2. So expression for Ksp is, first write down the equation. So Ca3PO4 twice solid reversibly gives 3 Ca2 plus aqueous plus 2 PO4 3 minus aqueous ions in the solution. So here number of moles of cations are 3 and number of moles of anions are 2, and with their charges, now if we consider, then the total positive and total negative charges are balanced, so our equation is correct. Now let's find out its Ksp. So Ksp is equal to active mass of By plus raised to x. By plus is our Ca2 plus ion now. So in the expression you will find active mass of Ca2 plus raised to 3. And for anion, active mass of Ax minus raised to y. Ax minus is our PO4 3 minus ion, and its coefficient is a 2. So finally the expression of Ksp is equal to active mass of Ca2 plus raised to 3 into active mass of PO4 3 minus raised to 2. So likewise you can proceed with other examples also. Now let's find out what is solubility and molar solubility. So solubility of a compound is the amount in grams that dissolves per unit volume. Unit volume can be 100 milliliters or 1 liter. Remember, 1 liter is 1000 ml. So you can take either 100 ml or 1000 ml of its saturated solution. So how much amount in grams are dissolved per unit volume, that is per 100 ml or per 1000 ml, is called as simple solubility. And what is molar solubility? Number of moles of that salt dissolves to give 1 liter of saturated solution. So number of moles per liter is called as molar solubility. So relationship between the two, they are related with each other by the term molar mass, as we know. So molar solubility, moles per liter, can be calculated as solubility in grams per liter upon molar mass in grams per mole. Now let's find out the relationship between solubility and solubility product. So consider a solubility equilibrium for BXAY, which we already considered. Ksp value is, Ksp expression is written, Ksp is equal to active mass of By plus raised to x into active mass of Ax minus raised to y. Now if S is the molar solubility of the compound, then the equilibrium concentrations of the ions in the saturated solution will be, for cation, X into S moles per liter. Remember, according to the equation, X moles of cations are present. So if S is the molar solubility, I have to multiply by X. So actual active mass of cation is X into S moles per liter. Similarly, according to the balanced equation, Y moles of anions are present. And so I have to multiply by Y to S to find out the active mass of anion, that is Ax minus ion. So active mass of cation is Xs moles per liter. Active mass of anion is Ys moles per liter. Now once we know active masses, let's substitute in the above expression and simplify. Therefore, Ksp is equal to Xs raised to x into Ys raised to y. Simplifying, expression becomes Ksp is equal to x raised to x, y raised to y, s raised to x plus y. So this is the very simple expression which we obtain if you remember this, what is x, what is y, and this final expression, you can establish a relationship between Ksp and S. Now on the right hand side, you will find the example of silver bromide. So AgBr solid reversibly gives Ag plus aqueous plus Br minus aqueous. In this case, x is equal to 1, y is equal to 1. So find out the expression of Ksp, substitute y is equal to 1, x is equal to 1. So expression is simply Ksp is equal to active mass of Ag plus into active mass of Br minus. S is the molar solubility of the compound. Now as X and Y are 1, what are the active masses of Ag plus and Br minus? They are simply S moles per liter for both. So in the ultimate expression, if I substitute X is equal to 1 and Y is equal to 1, I will end up with the simple relation which is Ksp is equal to S square. Let's consider one more example, that is example of PbI2, lead iodide. Now in PbI2, X is equal to 1, Y is equal to 2. And so substituting in the final expression, just to go through the final expression, X raised to X, so 1 raised to 1. Y is equal to 2, so Y raised to Y, 2 raised to 2. And S raised to X plus Y, so S raised to 1 plus 2. So upon solving, we will end up with the expression which is Ksp is equal to 4S cube. So this is how one can establish relationship between Ksp and S. Now let's consider ionic product of an electrolyte, IP, the product of concentrations of ions under any condition. That means when we carry out the experiment of qualitative analysis in the laboratory, in the test tube, we added OS, that is original solution of the given salt, and we are adding certain reagents. So in the test tube, what is the product of the concentrations of the various ions? This is called as IP, or ionic product of the electrolyte. And for the same case, if that is a precipitate obtained, that precipitate obtained means it is the sparingly soluble salt, so it precipitates out. That particular sparingly soluble salt has its characteristic Ksp, that is solubility product. So ionic, the product of the concentrations of ions at equilibrium conditions is Ksp. Now when ionic product is equal to Ksp, that is solubility product, then it is a case of saturated solution and solubility equilibrium exists. When ionic product is less than Ksp, then it is a case of unsaturated solution, precipitation will not occur. And when ionic product is greater than Ksp, it is a case of supersaturated solution and precipitation of the compound will occur. So this is called as condition of precipitation. Ionic product must exceed its characteristic constant Ksp, or must exceed solubility product, then only precipitation can occur. Let's consider one numerical. A solution is prepared by mixing equal volumes of 0.1 molar magnesium chloride and 0.3 molar sodium oxalate at 293 Kelvin. Would magnesium oxalate precipitate out? Ksp of magnesium oxalate at 293 Kelvin is 8.56 into 10 raised to minus 5. So a reaction between magnesium chloride and sodium oxalate is considered. So this gives us a precipitate of magnesium oxalate, which is a sparingly soluble salt. Now concentration of magnesium chloride is 0.1 moles and that of sodium oxalate is 0.3 mole per liter, of course. The equal volumes of both the solutions are mixed and the constant Ksp of magnesium oxalate is also given. When solution is prepared by mixing equal volumes, volume gets doubled and hence effective concentrations of ions would be half of the initial concentration. This point is quite important. When we increase the volume, concentration doubles. We saw the relationship between volume and concentration as C is equal to 1 upon V. So volume, if it is doubled, concentration becomes half. And so concentration of Mg2 plus ions is 0.1 molar concentration. of MgCl2 is mixed with 0.3 molar concentration of sodium oxalate. So total volume is 1 liter in case of MgCl2 and in case of sodium oxalate. So 1 liter of both the solutions are mixed. So total volume becomes 2, and so I have divided here by 2. So 0.1 upon 2, actual magnesium ion concentration is 0.05 moles per liter. Similarly, for oxalate ion concentration, 0.3 divided by 2, so it is 0.15 moles per liter. These ions would react to form sparingly soluble salt, magnesium oxalate, accordance with the reaction. So this is our reaction. Mg2 plus aqueous plus C2O4 2 minus aqueous reversibly gives MgC2O4 solid. Ionic product in the solution is given by IP is equal to active mass of Mg2 plus into active mass of C2O4 2 minus. Substitute the values. So concentration of magnesium ions is 0.05, concentration of oxalate ions is 0.15. So that comes out to be 7.5 into 10 raised to minus 3. Now compare with Ksp value. Ksp for magnesium oxalate at 293 Kelvin is 8.56 into 10 raised to minus 5. So ionic product is greater, 10 raised to minus 3 is greater than 10 raised to minus 5. So ionic product exceeds solubility product. So precipitation of magnesium oxalate occurs. Consider one more problem. Solubility product of silver bromide is 5.2 10 raised to minus 13. Calculate its solubility in moles per dm cube and grams per dm cube. Molar mass of silver bromide is given 187.8 gram per mole. Now solubility equilibrium is AgBr solid reversibly gives Ag plus aqueous plus Br minus aqueous ions in the solution. Solubility product is given by X is equal to 1, Y is equal to 1, so Ksp is equal to S into S, that is S square. So S is equal to square root of Ksp. So substitute Ksp value. So S is equal to square root of 5.2 10 raised to minus 13. So answer is 7.2 into 10 raised to minus 7 moles per dm cube. Now to calculate solubility in grams per dm cube, we have to multiply by given molar mass. So it is 1.35 into 10 raised to minus 4 grams per dm cube. So in this class, students, we saw what is a solubility product and how it works or how it is helpful in our practical chemistry. Thank you.